If you want to know quickly whether NumPy in pure Python on Android can actually support your project, this video is for you. First, we will show the Python code for some common and powerful NumPy features that I implemented on Android. Once you see the code, you will want to know how to build and test your app on Android. Head next to the section where I walk you through a build setup that is guaranteed to work without hassles. But first, here's the code for a working NumPy. Say that we want to capture the raw image pixels from your Android camera into a NumPy view. We start from a raw byte buffer and tell NumPy how to see it. Text is the live preview texture from Kivy's camera. So w width, h height is equal to text.size. Buff, which is the buffer, is equal to text.pixels. And then ARR for array, which is a NumPy array. We set it to NumPy.frombuffer, and we assign the raw pixels from the buff object, and the data type would be unsigned integer. And then we reshape it to a standard NumPy array object to represent the image itself, and of dimensions h for height, w for width. FromBuffer avoids extra parsing. It maps the byte string as unsigned integer. Reshape gives us a height times width times channel at dimensioned array with 4 channels. This is to allocate an RGBA object. We'll talk about this a little bit further. We will call this the image array, as this is nothing but the NumPy array that captured the image from the Android camera. At this point, your image array starts from the bottom left. That's OpenGL style, not the usual top left origin, which is used in subjects like computer vision. Flip the captured image array to top left origin because that's how we want to work with that object. Computer vision code expects row 0 at the top. We fix that with a view, but there is no copy, which is efficient. Note that the slicing operation that you see here reverses the first axis by stride. Now 0, 0 is top left. A computer vision library like OpenCV and the type of image processing math that we do might expect. Next, match on-screen rotation. The image that shows on your camera is what we call the preview canvas. We need to keep the NumPy image array aligned properly with the image preview that is showing on your camera. It's another thing that sometimes the image preview itself may rotate minus 90 degrees or mirror for the front camera. But that's a discussion for later. We use NumPy np.rotate90 method here. And you can see the code here. We obtain the angle and then examine if the angle is 90 degrees. Then we apply the np.rotate90 function on the image array to rotate it. And then you can see the code here that handles if the preview angle is 180 degrees or 270 degrees. Now, np.rot90 reorders views, small constant cost, and it keeps the math honest. The result, the saved or processed image lines up with what the user sees on the camera preview. To handle front camera quirks, selfie cameras are sometimes mirrored. In the Android camera object, a value of 1 for self.camera_index indicates the selfie camera here. I know I haven't introduced the Android camera yet, so just focus on the NumPy patterns for now, and the next sections in this video will give you a more complete picture of the Android camera system so that you can build your own app to run on Android. So back to NumPy here. For selfie camera, we set array_rot for rotation to receive the flipped image array to reverse the mirroring like so. You can see the np.rot90 for rotation at play here. NumPy memory management works on Android too. It keeps memory contiguous before uploading. The camera system has a texture object that provides camera image previews on your phone. We also use the texture object to write the NumPy image array as an image file to your phone's internal storage. So texture.blit_buffer expects a contiguous block of memory which NumPy ensures after mirror correction, image rotation, etc. As contiguous array forces a compact layout if we used strided views, that is, we used flips or the function that you saw, the method that you saw, rotation 90. 2 bytes gives a clean buffer of image bytes in the right color format, that is RGBA for the texture object to work on. RGB indicate the primary colors blue, green, and red, whereas alpha carries information on how transparent or opaque the image is. See how we create the alpha object using np.full. np.full returns a new array of the same shape as that of a gray image, where each element is set to 255. And each element of the array alpha is of type unsigned integer. Here the gray image is another example of NumPy image array. It is similar to the RGB image array you saw before, but it does not carry color information, that is red, green, or blue. So you can see that we can use NumPy np.full, np.stack, and np.concatenate methods to nicely add an alpha channel to the image array. You can also see that the np.clip method works well. It is used to clip the values of elements in an array to the limits of an interval. In our example here, that interval is 0 through 255. So the NumPy methods you saw in use are cheap, deterministic building blocks you'll reuse everywhere. Now that you have seen NumPy in action, let's make sure you can actually run this on your Android device. Coming up is the next section, which is about creating a build environment where you can test your Android app with the cool features of NumPy. Let me walk you through a build setup that is guaranteed to work without pain. If you want a proper Kivy installation for Android Python to build stable, crash-free applications, then this video may be for you. I made this video because I feel that the official instructions for Kivy Buildozer installation are not super clear on some essential steps for a solid build environment. Without these additional steps, the app that you build under Kivy Android can crash frequently even though your Kivy and Buildozer are installed normally. And you can find yourself spending too much time troubleshooting these crashes, whereas you really should be focusing more on what matters the most, designing and developing your app. I have a Ubuntu 24.04 LTS desktop Linux machine here, running under Oracle VirtualBox version 7.0.18. I chose Linux because that is one of the operating systems that allows compiling for Android as per official documentation. I've brought up a terminal in my Linux virtual machine. Python is usually installed as part of the Ubuntu Linux installation. Let's check the installed Python version. Version 3.12.3 was installed on mine. We need the Python 3.12 package installer, so let's install that first. Next, we're going to install a Python virtual environment. If there is one way to fix all kinds of startup problems, hard to debug crashes or compile issues for your Android APK under Kivy Buildozer, it is the installation of Kivy inside a Python virtual environment. The official Kivy installation instruction page merely says it is optional but strongly recommended to use a virtual environment, but I find that we must use a virtual environment. It is not optional if you hope to build stable Android Python apps in Buildozer Kivy. And the reason for this is explained on the Python documentation page here. Applications will sometimes need a specific version of a library because the application may require that a particular bug has been fixed, or the application may be written using an obsolete version of the library's interface. This means it may not be possible for one Python installation to meet the requirements of every application. The solution for this problem is to create a virtual environment, a self-contained directory tree that contains a Python installation for a particular version of Python plus a number of additional packages. Let's create a directory myapp for Kivy. For now, I'll give read-write-execute permissions to anyone accessing it so that we will not face permissions issues while installing the Python packages and modules for Kivy. Let's change to this directory and launch the virtual environment. Sorry, we need to create the virtual environment first. The virtual environment is now created. Let's activate it. We're now within the Python virtual environment. From here, we will now install Buildozer for Kivy. Okay, we need to also give Buildozer adequate permissions of .venv directory, the base location of our virtual environment configuration. Let's retry Buildozer install. Okay, the Buildozer install has completed successfully. This time it completed without any permission error. Next, we will use the Debian Linux Advanced Package Tool, or APT, to update our packages and their versions from the system or distributions repositories. We want everything updated to a nice baseline of package versions that we expect to work together. We will now install a list of packages or modules needed by Kivy. I'm going to copy and paste the entire command from this page here. Likewise for Python, I'll stick to the version recommended on the Kivy install page. We need to omit the user flag since we are installing Python in our Python virtual environment. Let's retry. Python is now created. If you want a separate video on installing a specific Python version, link is in the description. Let's configure our config file for bash environment with the path environment variable as instructed here. Next, we will install the automake utility. In Kivy's instructions, automake install is only suggested for iOS build. However, I find I needed to install it for Linux too from trial and error. For the next set of package installs, we need to change the system repository from which APT will download the packages. But before that, it is super important to know the implications of doing so. Here on this website, it says, being able to change the repositories used by your package management system is a powerful feature, but this power comes with some responsibility. Users are cautioned that it is possible to break your system in a way that it could be difficult or impossible to cleanly fix by adding third-party repositories or repositories for a Debian version that does not match your current version. These repositories create risk of conflicting package versions, creating what's sometimes called a Franken-Debian system. The whole concept behind a Debian stable release is that the Debian developers have picked a set of software and their versions that function nicely together. While this software is patched to fix security issues, the software is frequently not the latest version. It takes some experience to know how the repos may be changed without the risk of breaking your system. Users of all levels are advised to change repos cautiously. Therefore, if you change your repository for your specific package install within your Python virtual environment, install the required packages and then remove the repository change, immediately afterwards. To change the repository, we need to add a line to the sources.list file like so. Let's do an apt update. Next, we will install terminfo library, which is libtinfo5. Again, I found the need to install this package after trial and error. Here's some info on libtinfo5 on your screen. The command has completed. On mine, libtinfo5 was already installed during my mini tests. Next, we will install setup tools. Again, I couldn't find a step requiring installation of setup tools on this page. However, if you dig further, it is mentioned here. Finally, we can initialize Buildozer like so. We can see that Buildozer spec is successfully created, which is an indication that Kivy for Android Python has been installed. I've tested my Android APK, which I built on my Kivy Buildozer, and it works perfectly. Great! You now have a stable Kivy plus Buildozer environment. We'll quickly test it with a minimal app. This first app keeps NumPy out of the foreground, so you can validate deployment, permissions, and UI scaffolding without extra moving parts. Once that's working, the final section on Android camera architecture will connect the dots and show exactly where those NumPy operations plug into your Android workflow. But first, here's your working app for Android. If you are challenged by Android devices which cannot run OpenCV and heavy machine learning, there is a way out. You can run bare minimum OpenCV functions on the Android device and do the heavy machine learning on a server backend. This video is the third in our playlist of solutions to integrate OpenCV on Android. I will show you how to use Kivy Python and OpenCV to validate an image for processing, load image files on an Android phone, send that image file to a server for OpenCV processing, and have that server handle the image with OpenCV and Python imaging libraries. Our Android Python code reads an image file from the phone's external storage and sends the image file via HTTP post to a REST API. The server receives the image file and uses OpenCV and NumPy to process that image file. Let's first set up a Kivy Android application and the GUI for the phone, but if you want to dive straight into the REST API and OpenCV, you can fast forward to here. We begin by writing our root class MyAppRoot, which inherits from Kivy grid layout. For this class MyAppRoot, let us write a Kivy design file which specifies the graphical user interface layout of my app. Here is a visual map of how the widgets are laid out. Here, root refers to the root class MyAppRoot, which inherits from grid layout. MyAppRoot is referenced to draw the GUI on the screen, and root height and root width refer to properties of MyAppRoot class. I'm going to set the color and alpha channel values for this level widget. Then I'm going to add a box layout inside the top level grid layout. And it is going to have two widgets inside of it. So I specify two columns. One is a button and another one a text label that we will use to display some output from our program when we click the button. The on-press property of the button is set so that when we click the button, it'll call grab_send_img method of the root class. That root class is myapp_root. We will implement the grab_send_img method in a bit, but before that, let's set up the text label here. Let us implement an object property which we will use to send values from the Python program, and set with it the ID of the label here. For Python reference, we will name it img_size_label, and for Kivy reference, we will name it img_size_label_Kivy. And we will specify them on the two sides of the colon here. Just need to fix the indentation here. Next, we have to implement the grab_send_img method in myapp_root class. Before that, we need a class myapp that inherits Kivy app, because ultimately we want to launch our app as a Kivy app. Its build method instantiates the myapp_root widget class and launches the app. To put everything together, we finally have to instantiate myapp. Let's implement a callback function to handle internet and external storage access permissions. Let's define a global variable last_permission, which will be used to signal if permissions dialog was served to the user. Note that the permission handling code can be more robust in that we have not implemented the scenario where the user does not give permissions. This is a topic for another video. Let me know in the comments if you'd like another video. For this video, I want to keep things simple, so the code only supports a scenario where the user gives necessary permissions. Essentially, it works. Now, on to the implementation of the grab_send_img method in myapp_root class. First, a simple check for user permissions to use the internet and device external storage. I'm picking up a file named more_digits_plot.png from the DCIM subdirectory of the device's external storage. For testing purposes, I manually dropped this PNG file into the DCIM directory of the device, which I am emulating in Android Studio. We open the file to read all the bytes and encode the data in base 64, which is recommended for sending the data by HTTP post request. If you're liking the content so far, then please give us a like. This will motivate us to make more content like this, and your likes will help us reach our channel to many more viewers in the community just like you. Next, we set up a JSON to send the file name and file size. This is not strictly necessary, but helpful information to validate the information received at the server side. Then we set up the HTTP REST connection to the server, where we will upload the PNG file with an HTTP post request. I won't go into the details of this. If you're interested, I've provided a link to another video in the description. I'm going to do a JSON dump to send the base64 encoded contents of the PNG file through an HTTP post. JSON key img points to the base64 encoded file contents. It is important to set the key correctly because the server will use the same key named img to retrieve the base64 encoded image file contents from the incoming JSON. I'm going to set the label with the status of that upload request. Remember, we set up img_size_label to communicate that to the widget in our myapp.kivy file. Along with the status, we will also report the shape of the NumPy array returned when OpenCV-IMRead function loads the PNG file. This is in the Android phone. We're using flag 0 in IMRead to load the image in grayscale. I'm going to set up some exception handling too in case something goes wrong with the HTTP post request. And some code fixes, some typos, etc. The APK is built and ready to be deployed. We can deploy the APK to Android Studio, where I already have an Android phone emulation set up. But the APK will fail as soon as it makes an HTTP post request to send the image file, and this is because there is no server-side code implemented for this REST API to grab the image file. So before we deploy the APK, let's implement the server-side code to grab the image file and apply OpenCV and NumPy image processing to it. Let's open the Flask Python script on my server side. I'm using Python Anywhere hosting service for this. Let's get the required imports first. The Android client we wrote is going to send data in JSON format. We also need Python imaging library or PIL services to add image processing to our Python Flask script. Next, let's map our URL for HTTP post to a Python function. This function will handle the logic of receiving the image from our Android client as a JSON payload and machine learning related image processing with OpenCV and NumPy. We'll abort with an HTTP 406 error response if the payload is not valid JSON or if the JSON key img is not present in the JSON. Remember that the JSON key img points to the base64 encoded image file content which we want to retrieve here. If all looks good, then we will access the img key to access the payload and decode the data. from base64 encoding into bytes. Then we will instantiate a Python imaging library object from the decoded bytes. We will write the decoded bytes to the server's file system. This should restore the image contents into the original binary format of a PNG image file. Let's get a NumPy array from the PIL image object, and using OpenCV obtain a NumPy array from the PNG, a file that we just saved to the server's file system. We are using flag 0 in IMRead to load the image in grayscale. The array shapes should be the same for the PIL image and the PNG file in the file system if the image was transmitted and captured correctly. We will check this after we run the app and generate some logs. Okay, some code fixes here. Let's reload the website, which will compile our Python Flask script. Now let's go to Android Studio, launch the APK there. Let's press this button here, which should set off the process showing on your screen. That is, grab a PNG file from device storage, encode it in base64, and send it to server via HTTP post. Looks like we got a success response from the server. Let's check these server logs. Looks like the server handled the HTTP post without errors. We can see that the NumPy array shapes for the PIL image and the PNG file in the file system are the same. This serves as a validation that the PNG image was transmitted by Android program on the phone and processed by OpenCV on the server correctly. I have shared the code in the description box below. So in summary, we have shown a way to use the power of OpenCV image processing and machine learning by distributing the load between an Android phone and the server side, where the real power of OpenCV, Python imaging libraries, and NumPy can be unleashed for heavier machine learning. Hey, give us a like if you found the content useful. Please share with your friends and let us know in your comments if there's something we can improve on, or if there is another topic you want us to make a video on. Help us reach our channel to more viewers who could find our content useful. Peace. Remember, at the start, we already proved NumPy runs on device. The server path you just saw is one option in the toolbox, useful when phones are weak or you need heavier models offloaded. Now, let's see how our challenging but fruitful journey helped us understand and build our computer vision architecture, where we have used NumPy within Android. Textures, providers, watchdogs, promotion, the building blocks that make the magic possible. If you are in that place right now where the preview vanishes, logs stay empty, and you're wondering whether this whole Python on Android thing is worth it, it is. You just need to see the map behind the mess. Textures, providers, watchdogs, promotion, the building blocks that make the magic possible. You know the moment when you're sure the code should work? You run your Kivy app, hit build, deploy to your phone, and the screen just sits there, black, silent, mocking. No crash, no error, just nothing. I've been there. I actually thought my phone's camera was dead. That quiet failure, it's almost personal. So I decided I wouldn't sleep until I knew why. My first clue came from one tiny word in the docs, texture. At first, I ignored it. It sounded like something to do with art, not code. But the more I looked, the more it felt alive. Every frame from the camera is really just a texture, a small beating block of pixels updating in memory. When the screen went black, it wasn't Kivy's failing. The heartbeat had stopped. The texture wasn't updating. I remember thinking, oh, so the bug has a pulse? Okay, texture found. But why did one phone behave and another just ghost me? That's when I met the idea of providers. Android APK for Kivy, little translators between hardware and Python. And suddenly it made sense. My code wasn't wrong. My translator just didn't speak that phone's dialect. That was a relief. For once, the problem wasn't me. But then came the quiet death. The app stayed open, the feed just stopped. No errors, no warning. I remember staring at the preview, waiting for motion. That's when the term watchdog showed up in a GitHub issue. It's not magic, just a timer that asks, are frames still coming? If not, restart the feed. Simple, but it felt like CPR. For the first time, my camera could recover instead of crash. Each fix taught me something new. Textures give you life, providers give you language, watchdogs give you time. But the real piece came with promotion logic. A ladder that says, if one provider goes silent, another steps in. No alerts, no manual restarts. It's like teaching your app to trust itself. Looking back, I spent weeks fighting symptoms that weren't really bugs. They were lessons, each failure revealing how the camera ecosystem actually works. I used to dread the blank screen. Now I see it as feedback. The system telling me where the chain broke. That shift from panic to curiosity changed how I built everything in Kivy. So, if you are in that place right now where the preview vanishes, logs stay empty, and you're wondering whether this whole Python on Android thing is worth it, it is. You just need to see the map behind the mess, textures, providers, watchdogs, promotion, the building blocks that make the magic possible. In the next video, we'll take that map and plug in OpenCV to finally make image processing work with the camera, not against it. And when you're ready for the full engine, the one behind every demo you'll see here is waiting for you on my premium content, because nobody should have to fight the black screen alone. Link provided in the description below. What if Camera for Kivy isn't available? You still need a dependable path. What happens when you can't use Camera for Kivy? Maybe your build keeps failing, your client's app can't include the dependency, or your Python for Android environment just refuses to run on your particular Android build. That's when you realize you still need a working camera pipeline for OpenCV, but all you've got is the classic Kivy camera. In this episode, we'll look at how that fallback actually works, what you gain, what you lose, and when it's still the smartest move. If you've been following the Kivy OpenCV Vision Stack series, you already know the 4 core switches that define feed reliability: texture, provider, promotion, and watchdog. The classic Kivy camera only gives you 3 of them. Let's unpack what that means under the hood. Even the classic camera follows the same architectural skeleton. It still uses a provider like Camera Android or Camera G streamer. Every frame ends up in a texture, which is what you actually see on screen. There's even a bit of promotional logic happening automatically. Kivy quietly checks which providers are available and promotes whichever one reports that it's compatible. The missing piece is the watchdog. If your feed freezes or buffers stall, nothing automatically resets. You'll need to handle that manually. It's a simpler design. Even without a watchdog, you can absolutely use this path with OpenCV. Instead of relying on CV2 video capture, you pull the texture's raw bytes yourself, convert them into a NumPy array, and then feed them to OpenCV. This method works consistently across Android builds, no hidden dependencies, no extra provider required. The trade-off is performance. Because each frame crosses the GPU to CPU boundary, expect lower frame rates. That's the cost of control, but what you gain is stability and full visibility into what's happening with your feed. So when does the classic Kivy camera make sense? Use it when camera for Kivy isn't viable. Maybe you're locked into a specific build pipeline, or you just need a stable path for using OpenCV. It's also great for snapshot-based tasks, logo detection, static measurement, or frame-by-frame verification. It's not the fastest option, but it's reliable, minimal, and surprisingly resilient. Now that we have looked at the fallback route, we're ready to compare it side by side with camera for Kivy. In the next episode, we'll measure real OpenCV workloads on real Android hardware. Subscribe if you're building for Android with Kivy and OpenCV. The NumPy methods you saw in the beginning of this video help us integrate the Android camera with OpenCV, a powerful computer vision library. Subscribe to our channel and follow our playlist to learn more about how we implement NumPy for computer vision with OpenCV.